4. We're near the end of the chapter 2 in the notebook, and we'll start with what I call the spin dance, but it's really how we get the spins to move with our control. And the way we do that is we take advantage of the torque equation on the magnetic moment, and we apply this in the rotating frame. We apply we call it B1, or it's an RF magnetic field, a radio frequency magnetic field. We apply that at the Larmor frequency so that there's no effect visible in this rotating frame of the main magnetic field, but we see an effect of this applied B1. And this B1 field can be relatively small. But if you take these equations, and we'll probably write these out, and then solve for the magnetization as a function of applying this B1, and the net effect will be, it will precess around B1. You can expect that because that's what this equation says it will do. And so that's how we can apply a radio frequency magnetic field, and we can get the spins to then tip to any desired angle by applying that for a fixed amount of time and turning it off when we're happy with how far it's tipped. So that's the RF excitation. We'll spend some time on that. We've already talked about the Boltzmann distribution and thermal equilibrium. So that's this part of chapter 2. You'll recognize the relationship we come up with. And finally, in this chapter, we're going to talk about relaxation. And the concept here is, unless we have something else going on, we won't have any magnetization being changed. It'll just precess according to our applied fields. But in real life, there's a lot of interactions going on between our magnetic moment and either magnetic moments or other sources of magnetic fields that are fluctuating around it. And these fluctuating fields cause our magnetic moment to return to its thermal equilibrium state. And you can expect that that's what it would do. And so there are these time constants, we call them T1 and T2. T1 represents the relaxation time constant of the Z component of the magnetization. The Z component, remember, is unique in that it's in the direction of the main magnetic field. So we define the direction to be that, and so the change in time of the Z component of the magnetization is given by this relation, and it relaxes with the time constant T1. And the transverse component, and I write this as M, X, or Y, relaxes with time constant T2. Now, we'll talk more about that in this, because in fact, there are several processes that enter into T2, which means actually that T2 is much shorter, or somewhat shorter at least, than T1. T2 can be very short, so the time at which the magnetization stays in the transverse plane with the time that it stays there can be very short, and it relaxes, like I said, with T2. There's with the other components of T2, we'll talk about reversible and irreversible relaxation, and that's all coming up. So this will give you we'll get to the end of our chapter 2 and then move on to more and other exciting things.